Hello everyone, welcome to our channel Code with Sunny, and today we will be discussing the easy problem, that is a daily LeetCode challenge problem of January 25. The problem name is, you can see over here, valid mountain array. Its index is 941. Okay, so basically this problem involves brute force, you can also say. So that is, we have to just check it out whether the given array is a valid mountain array or not by just iterating over the indexes from left to right. Okay, so I will just tell you the best way to solve this problem. For now, first let's understand what this problem is going to signify. Okay, so recall that array is a mountain array if and only if the length of the array is strictly greater than 2, and there exists some index I that is not among the bounds of this array, and the that is first I elements, you can see up to the index I is going to be strictly increasing, and the rest of the elements after that index is going to be strictly decreasing. So then the valid like the array is called the mountain array. If you are not getting this right now, no need to worry about. I will explain it with the help of examples. Okay, so let's look over the constraints. You can see the length of the array is going to be at most 10 raised to the power 4, and array values is also at most 10 raised to the power 4. Okay, so let me just explain this concept in the simpler words. So let me just write down valid mountain array. Valid mountain array. Okay, so when the array is called a valid mountain array, so an array is called a valid mountain array if n, which is the length of the array, is going to be like greater than or equal to 3. Okay, and the array elements satisfy this condition: a0 less than a1 less than a2, and it goes on up to the index I less than ai. Okay, note that I must be lying within the range n minus 1 and 0, like I must belong to 1 to n minus 2. That is the range. Okay, and all the elements after that, that is ai plus 1, should be strictly decreasing. Note that the term is strictly decreasing, and it goes on up to the a of n minus 1. So if the array elements satisfy this criteria for any index I, then the array is called a valid mountain array. Okay, now how we are going to solve this problem efficiently? So the very first approach is going to have a O of n square time. You can easily see how we are going to do that. Fix any index I, not calling it as any, fix every index I, note that valid index I, am talking about those index I which are lying in this range. Fix every index I and check it out. All the elements that are in the range from 0 to I minus 1 are going to follow the criteria of strictly increasing, and let me write down si denotes strictly increasing, and all the elements which are in the range I plus 1 to n minus 1 is going to follow the criteria of sd, strictly decreasing. Note that we are going fixing every index I and iterating for all the elements again. So fixing every index I takes O of n time, and for every index I we are iterating the almost entire array, so the time complexity would be O of n square. But can we do this better, like in better time? Because O of n square is not going to pass, for n is at most 10 raised to the power 4, so the iterations goes up to around 10 raised to the power 8. So the solution will give the verdict we are going to get is TLE. So can we improve our this O of n square time code? Yes, obviously we can improve that. Okay, so you can focus it over here is that there must exist one index I, so that the array is called a valid mountain array, right? So can we just find out that index I? Yes, we can find out that index I. So what we are going to do is we are going to start our index from 1, and we will check it out. Let me write down a while loop condition. While index is going to be strictly less than n, and array of index is going to be strictly greater than array of index minus 1. Okay, now this is going to be like quite tricky. If you are not getting it, no need to worry about. Let me just bold it up. So this is actually the thing that I'm going to do. So I will find out that index I, which is going to be the peak. Okay, so while index is less than and array of index, that is the current value, is going to be strictly greater than the previous value. You can see a1 is going to be greater than 0, then I will move out to the next index until we are going to find that index which which doesn't satisfy this criteria. So you can see if ai is the index, that is the peak, so this iteration will stop when index reaches this position ai plus 1, because if index it over here, then this is going to be greater than the ai minus 1, so this will hold. But when index reaches to ai plus 1, that is the value corresponding to the I plus 1th index, then you can see this while loop will break, so my index will be at here and the peak position will be at this position, right? Now what we are going to check again is whether all the elements lying over here is going to follow the strictly decreasing pattern or not. Okay, again we are going to do the same condition but with slight modification. So index less than and array of index is going to be strictly less than the array of index minus 1. That is what we are going to do, because we need to check the strictly decreasing part. Okay, now if again after doing that index reaches to the last position of this array, that is nth, note that if it is 0 based indexing, I need index will always reach up to this position n for a valid mountain array. Okay, so yeah, yes, when it reaches to the n, yes, we can say yes, there exists a valid mountain array. Okay, note that there must exist a strictly increasing pattern and a strictly decreasing pattern. So we will be using a boolean variable to check it out whether we have encountered the case of strictly increasing and strictly decreasing or not. Okay, so without wasting our time, let's look out the code and understand what we are going to do efficiently. Okay, so I don't know what I've clicked. Yeah, you can see first I have got one wrong answer because of one of my foolish mistakes. Okay, so no need to worry about. So time complexity would be O of n, space complexity would be O of 1. Okay, so we will start from index equal to 1, where n is now the array size, and found 1 will denote whether we have found a strictly increasing sequence before the peak, and found 2 will denote whether we have found the strictly decreasing sequence after the peak. So while index less than an array of index is strictly greater than the previous value. Okay, it means that still we are encountering the strictly increasing sequence before the peak. So we are going to increment our index up to the case like whether we are not done with the strictly increasing sequence. Okay, so found 1 will become true because we have found a strictly increasing sequence. And when this loop breaks, we need to check it out whether we have found a strictly decreasing sequence or not. So again, index is less than an array of index must be less than the previous value, that is index minus 1. Okay, then again index goes to the next position and found 2 becomes true, denoting that yes, we are going to have a strictly decreasing sequence. Okay, and what is the criteria of a valid mountain array? There must exist a strictly increasing sequence before the peak, and there must exist a strictly decreasing sequence after the peak. You can see found 1 must be true and found 2 must be true. Also, there exists at exactly one index I. Before that, all the elements follow a strictly increasing sequence, and after that all the elements follow the strictly decreasing sequence. In that case, you can see our index variable must have the final value as n. Then only we can say that yes, this array is a example of valid mountain array. So this will give you all test cases passed. So if you guys have still any doubts, do reach out to us in the comment section of the video, and do not forget to subscribe, like my videos, and thank you for watching this video.